and kind of take you through some of these. So remembering with your triangle inequality, first of all, the angles of a triangle always add up to 180, but also that the smallest angle is opposite the smallest side. And the largest angle is opposite the largest side, the longest side. Okay, so what we're doing here is we want to go ahead and order the triangles, or the lengths of the sides of the triangles, from longest to shortest. So this is one of the things you always want to pay attention to, is the order. So I'm going to look for the largest angle, and that's right here, and the angle opposite that is Pythagoras trail. So this is Pythagoras trail. Okay, and then our middle angle right across, here's Euler trail. And then my last one is Archimedes. So we, just like using angle lengths to find side lengths, we can use side lengths to find the order of angles. So here we're ordering from smallest to largest. So here we're going to find the smallest side, and the angle opposite that is angle R. And then the next one, angle Q, and then angle P. Okay? So when you're given two lengths of a triangle, I'm going to write this down. Given two lengths of a triangle, the third side is in between the sum and difference of the given two sides. So I take these two side lengths, right, and I add them together. So I have 42 plus, I subtract them first, I'm sorry. I subtract them and I do 42 minus 20, and then I know that side length is in between the sum and the difference. So it's in between 22 and 62. Now it can't be equal to those two, so it has to be greater than 22, so, and less than 62. So these are the three angles that are the three side lengths that actually work. Okay? So when you're given three side lengths, you want to make sure the sum of the two smallest sides is always greater than the third side. Okay? So, okay, so let's take another one. GF is equal to 15, right? HF is 13. So what's the range of values for this last one? So it's in between 15 minus 13 and 15 plus 13. So that's in between 2 and 28. So that's the answer there. Okay. Now, when you're doing these overlapping triangles and you're trying to do triangle congruence, I would strongly suggest that you separate them. So we want to do A, B, C, right? So I have A, B, C. So here is A, B, C. And then D, C, B, triangle. I'm going to do this right here. Sorry. D, C, B. All right. So first thing, we know that BC is congruent to itself by the reflexive property. And then we say that AC is congruent to BD. Well, that's wonderful. So now we also know that AB is parallel to CD, and that AB is perpendicular to BC. So because these are parallel, these two angles are same side interior, right? Because these are your two parallel lines and this acts as your transversal. So these are same side interior, and remember that same side interior are supplementary. So if this is 90 degrees, then this one also has to be 90 degrees. So this tells me that there's two right triangles. Now, how am I going to prove these two triangles congruent? So when I have a right triangle, I'm going to always check, do I have the hypotenuse? I do. Do I have another leg? I do. So the answer is E, by hypotenuse leg. Okay? The other, make sure that you check, make sure that it's always the hypotenuse is one of the sides. Okay? It's like the side-side angle theorem, but with right triangles. Okay? You can't prove triangles congruent with side-side angle, but you can if they're right triangles because of the hypotenuse leg theorem. The coordinate values of these vertices, MLK, right? We want to make a triangle congruent to triangle MLK to LMN. So one of the easiest ways to do this is, if you notice, they're going to share this side, LM, right? And if I look here, I have 1, 2, 3. K is 3 points up. So if I go down 3 units, I can make that N. And that is a perfectly congruent triangle. Okay? So that's always a good way to do it. Okay? All right, so let's move on. Now, if we're making these triangles congruent, so remember that the corresponding angles are congruent to one another and corresponding sides are congruent to one another. And when we're doing this, order is always so important. So here, I know that angle S is congruent to angle X. So this is congruent to this, right? And then I know that angle T, which is right here, is congruent to angle Y, and angle Y is right here. Okay, so now I can solve for N. So I'm going to do N plus 53 is equal to 77. So I'm going to take away 53, and I get N is equal to 24. Okay, so that's N. Now I need to figure out what M is equal to. Well, if I know that ST right here corresponds with XY, so where's my XY? XY is right here. So ST and XY are congruent to each other. So I would set up an equation, M plus 6 is equal to 14 minus M. And then I just do the algebra where I add M to both sides, and I get 2M plus 6 is equal to 14. Then I subtract 6 from each side, so I have 2M is equal to 8, and I divide by 2, M is equal to 4. So there's our M. Okay? Now, moving on. We want to do a proving triangles congruent here. So one of the things that I think is important, again, when you have overlapping triangles, let's highlight the triangles that we're trying to prove congruent. So I have QSR. QSR is one of them. QRS. And then I have TRS. So this is T, and it doesn't have to be beautiful, as you can see. TRS. Now, these guys, we're given that QSR is congruent to TRS. So TRS, that is congruent. All right. And then we say that PR is congruent to PS? Well, that just tells me it's an isosceles triangle, right? So if I know these two legs are congruent, then these two base angles are congruent. So now I can say that angle QRS is congruent to TSR, and that's by isosceles triangles. So I'm working out this proof before I write anything down. And I think that's important. The other thing you always need to remember is that these guys have an overlapping side. So they both share this side. So when I look at this, I always label these in parts. So is this an angle or a side? This is an angle. Is this an angle or a side? This is a side. And is this an angle or a side? That's an angle. So that tells me that's why my triangles are congruent, by angle, side, angle. So let's go back to this. So all this stuff was given to us, and then we said that TSR and QRS are congruent, and that has to do with the base angles of an isosceles triangle. So we're going to do base angles of an isosceles triangle. Now here, SR is equal to RS. They're exactly the same thing, so when something is congruent to itself, that is always the reflexive property, okay? And as you can see right here, I already figured out what it was. Angle, side, angle. So one of the things that you want to make sure you understand too is if I hadn't drawn out my triangles, I probably would have made a mistake and thought that these were part of the triangles that I was using, and that is not the case. Okay? So, moving on, we have triangle similarity. So, when we have triangle similarity, remember that the sides are proportional by the same scale factor, and that the angles are congruent. So when we have overlapping triangles right here, so this is one, and then there's this larger one right here, we have, do you see that they are actually sharing this angle R, right? So this angle is already there, so angle R is equal to angle R, but we're trying to prove by side angle side. So one of them has to be that that angle is congruent to itself. And then we need to say, okay, this side over this side is equal to this side over this side, because they have to have the same scale factor. So I have RQ over PR. So it's like the small one over the large one. So I have RQ and PR. These are corresponding sides. And then I can see that PT is the largest one here. Over, oops, nope, that doesn't work either. Okay, so let's try PR and QR, yep, over TR and SR. So remember, this is big over little, this has to be big over little, so this is the one that works. These are always very tricky, so be very careful. Okay, so select each set of numbers that could represent sides that are side lengths that are on MNO. Now, in order to do this, the ratio has to be the same. So I'm going to use some quick calculator tricks to help me out. So I'm going to use the first one. I'm just going to go from one to the other. So the first one is, I'm going to use the largest side here, and that's, I'm going to use my alpha y equals to make a fraction, and I do 18 over the largest side here, which is 7. Okay, and I get 18/7. Okay, well that doesn't help me a lot, but let's try, I'm sorry, it should be, that's not the largest one, it should be 21, sorry. So I'm going to do alpha y equals and do 21 over 7. Let me just clear this out. So I'm going to do alpha y equals and do 21 over 7, and notice that that reduces to 3. And then I do 18 over 6, and that reduces to 3 as well. Now I have to see if 10.5 over 2.5 reduces to 3, and it does not. So we go ahead, and that one does not work. So let's try the next one. Let's do 21 over 16. Sorry, alpha y equals, let's try it again. 21 over 16, and that doesn't reduce. And then let's see, 18 over 13. Now these still don't, oh Lord. If I do this, 18 divided by 13, these still don't reduce, so again, these aren't going to be the same fraction. Let's try another one. So we don't even have to do alpha y equals. Let's just do 21 divided by 14, right? That's 1.5. Then 18 divided by 12 is 1.5. And then I'm going to do 10.5 divided by 7. Since these ratios are all the same, this one works. So let's try the next ones. 21 divided by 2.1 is 10. 1.8 divided by, 18 divided by 1.8 is also 10. And then 10.5 divided by 1.05 is also 10. So that one works. So what I'm doing is I'm taking largest divided by largest, middle divided by middle, and smallest divided by smallest, and making sure that these ratios are all the same. So let's try the next one. 21 divided by 10.5, I think that's 2, and then 18 divided by 9.5, that is 1.89. So that does not work. So as soon as I get a ratio that's not equal to the one before, then I can stop. So then I'm going to do 21 divided by 4.2, and I get 5. Then 18 divided by 3.6 is also 5. And then 10.5 divided by 2.1 is also 5. So this one works. So we have 3 of these that actually work. So you have to work through every single example. So be very careful. All right. The coordinate values of the vertices of BCA are integers. Plot a point D that would make BCA similar to ACD. So BC's length is 2, right? And AC's length is 1, 2, 3, 4. Okay, so this is 2 and 4. So I know that BC is equal to 2 and AC is equal to 4, right? And these are corresponding sides, right? So 4. So the ratio has to be 1/2. So I need to see, I know that CA is equal to 4. So I need a CD that's going to give me a ratio of 1/2. So it's going to be 8. So this is going to have to be 1, 2, 3, 4, and then twice that. 1, 2, 3, 4. So this is the point because this length has to be twice of what the smaller corresponding side is. That one's tricky. Take a step back and look at it a couple of times and try to draw it out again. Okay, so let's look at the next one. Now, remember, identifying 3 segments that are a right triangle. Remember, we have a squared plus b squared equals c squared. We also have what's called Pythagorean triples. One of those triples is a 3, 4, 5. And then another is a 5, 12, and 13. Because if I had 5, 12, and 13, 5 squared plus 12 squared, is it equal to 13 squared? Well, let's see. 5 squared plus 12 squared equals 169, and 13 squared is also equal to 169. So I would strongly recommend that you guys memorize some of these Pythagorean triples. I knew this because this is a Pythagorean triple. So 3, 4, 5, 5, 12, and 13 is also a Pythagorean triple. And I would look up some of those and memorize them because they're very prevalent on the SAT as well. Okay, so now we're going to get into special right triangles, where we have, and some trig as well. So remember that we have two special right triangles. One is a 45, 45, 90 triangle, where the two legs are exactly the same, right? And the last leg is the square root of 2 times, the hypotenuse is the square root of 2 times one of the legs. When you have a 30, 60, 90 triangle, remember everything's in terms of the smallest side, which is, because we know the triangle inequality is opposite the 30 degree angle. So the way I describe those is, this is B, and then this is B times the square root of 3, and this is 2 times whatever this length is. So let's go ahead and look at this. Now, this is a 45, 45, 90 triangle. I know that because I'm filling in all these here, right? So if this is 10 times the square root of 2, look at this pattern right here. Do you see how these two sides have to be 10? So this length right here is 10, as is this one, right? Now, this one right here is a 30, 60, 90 triangle, right? So this is 2 times the smallest side. So I go down here and find the smallest side. The smallest side is 2 times something is equal to 16. Well, what's 16 divided by 2? That is 8. All right? So what is the height in feet of the flag? So if this is 8, then this one is going to be, this whole length is 8 times the square root of 3, right? But we're just trying to get the flag. So we're going to take away this 10 here. So it's 8 times the square root of 3 minus this 10 right here. So there you go. A way to remember that is that because we have 3 different angles in a 30, 60, 90 triangle, that's why I multiply by the square root of 3. That's how I remembered it. And then if you have 2 different angles in a 45, 45, 90 triangle, this is why I multiply by the square root of 2. Now, here's a right triangle, and we're going to use right triangle trig to go ahead and find our angles. So remember, we have SOHCAHTOA, which is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So when I do this, I always mark my angle. And I always pay attention to which one's the hypotenuse. This is the hypotenuse because it's always opposite the right angle. Now, according to this angle, this side is opposite. So which trig ratio gives me opposite and hypotenuse? And that is sine. Now, when I'm trying to find an angle measure, I'm going to use second sine, and I'm going to do 25 over 52. So I get making sure that my calculator is in degree mode, I'm going to do second sine of 25 divided by 52, and that gives me an angle of 28.7, which is close to 29. So making sure that your calculator is in degree mode is so important, so please make sure that you do that. Okay, now moving on. We're going to go ahead and go into this one. Here is where we're trying to find another value, okay, and this is a side length. So we're not going to use the inverse trig functions, we're going to use the regular trig functions. So again, we're going to mark our angle, all right, and according to this angle, this is the adjacent side and this is hypotenuse, right? So remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So I have an adjacent and a hypotenuse, so I'm going to use a cosine. So I remember that the cosine of 52 is equal to the side adjacent, which is 4.5 divided by the hypotenuse. Now I don't know what the hypotenuse is, but one of the keys to doing this is when you're solving for x is you can multiply both sides by x, but the way I do this is I remember that x is equal to 4.5 divided by the cosine of 52. Okay, so that's what I plug into my calculator. So again, making sure that I'm in degree mode, I'm going to quit out of that and I'm going to do 4.5 divided by the cosine of 52. Again, that's a ratio, so that's 7.3, and there we go. All right, so hopefully that makes sense. Another way to look at this is also understand this is going to be the longest side of this triangle, and this is going to be the shortest side, okay, because this angle would have to be 90 minus 52, which is 38. So this side has to be greater than 4.5. So we could rule out these two already just by using the triangle inequality. So please don't give up hope if you start to get discouraged and like, oh, I can't remember how to do this. All right, and these trig ratios are on your calculator, on your formula sheet. So I'm going to keep going for a little bit. I feel like we're making some good progress. So one of the things that we have to remember with rhombuses is that there's lots of properties with rhombuses. So let's talk about them. So with a rhombus, all the sides are congruent, okay? And the angles are not congruent, but the diagonals are perpendicular. All right, and then the diagonals bisect the vertex angles. So one of the things that I have to do is solve for x and y. So since I know that all the sides are congruent, I know that these two sides are equal to one another. So I'm going to set 4x minus 13 equal to 2x plus 1. I'm going to subtract 2x from each side, and I've got 2x minus 13 is equal to 1. I add 13 to both sides, and I get 2x is equal to 14, and I divide by 2. So x is equal to 7. So there's 7. Okay? The next thing I need to realize is that my diagonals bisect my vertex angles. And remember, bisect just means cut into two equal parts. So if this is 37 degrees, so is this, right? And I know, as I've already said, these are all perpendicular, so this is 90. We know that the angles of a triangle add up to 180. So if I did this, and I did 180, 180 minus 90 minus 37, I know this angle is equal to 53 degrees. So I just set 2y plus 3 is equal to 53. I subtract 3 from each side, and I get 2y is equal to 50. And then I divide by 2. So y is equal to 25. So here's our y. Okay, so there's always a trick to these. So remembering things that you can copy distance using things like rise over run and stuff like that, I just want to make sure you understand that. So the diagonals of a square intersect at a point at -3, -2. So at -3, -2, this is where they intersect. One of the vertices of the square is located at -7, 2, so it's up here. Okay, now remember, with a square, all sides are congruent. All diagonals are congruent. All the angles are congruent. And since the diagonals are congruent, they bisect each other too. Diagonals bisect each other. Right? So I know that this distance is the same to each vertice. All right? Now, find the vertex ABCD that lies in the first quadrant. So I have to be a little bit tricky here. Remember, this is 1, 2, 3, and 4. So I want to go over here. All right? So to get here, I go up 1, 2, 3, 4, and then I go over 1, 2, 3, 4. Now, what I'm going to do to get to the other vertex is I'm going to go up the same distance because it's a square, right? And then I'm going to go to the right, the other distance. So I'm going to go up 4, and instead of going to the left 4, I'm going to go to the right 1, 2, 3, and 4. And there's our point. Okay, so you're just copying it, just paying attention to what quadrant they want it to be in. All right, identify the quadrilateral with the following property. Well, a rectangle, a square, and an isosceles trapezoid all have congruent diagonals. So be careful, make sure you review the properties of all the parallelograms and trapezoids. Not hard, just a memorization thing, but they're kind of fun to work with, so hopefully you can do that. Okay, so now remember that the measures of the interior angle sum of a polygon is always n-2 times 180, right? The exterior, this is interior. The exterior angles always add to 360. So if you want to get one exterior angle, and there it's a regular pentagon, which means anything regular means that the sides and the angles are all congruent. Okay, so what is the measure of each of the angles right here? So first thing what I'm going to do is find one interior angle measure of a pentagon. So in order to do that, I'm going to take n-2 and I divide it by the number of sides because that's the angle sum, and if they're all congruent, I'm going to divide it by the number of sides. So there's 5 angles here, so I have 5 sides, and I take away 2 and I multiply that by 180, and then I divide it by 5. So that's really 3 times 180. And then I divide it by 5, and each one of these is 108. So this angle right here is 108, right? Now, I know that these are going to add up to 180. So I can set up a really nice little algebraic equation where I do x plus 108 equals 180. Now, you could probably do some fancy math without having to set up the algebraic equation, but I'm just doing it because I like algebra too. So 2x plus 108 is equal to 180, and then I subtract 108 from each side, and I get 2x is equal to 172. Sorry about that. I'm not adding and subtracting very well. Then I divide both sides by 2, so x is equal to 36. So each one of those adds up to 36. So Samantha is comparing two regular polygons, a triangle and a nonagon. Which statement is false? Okay, so let's look at this. The sum of the angles of a triangle is 180. The sum of the interior angles of a nonagon is 9 minus 2 times 180. So that is 7 times 180. So 7 times 180, that's 1260. So this is greater than the sum of the interior angles. That's okay. The measure of one interior angle of a nonagon is greater than the measure of one interior angle of a triangle. So if I know the sum is 180, I divide it by 3, so that's 60. And then I'm going to take 1260 and divide it by 9. Now that's 140. So that is greater. So that also works. The measure of one interior angle of a triangle is greater than the measure of one exterior angle of a nonagon. So let's try this. One interior angle of a triangle, that's 180 divided by 3, so that's 60. And now to get the exterior angle of a nonagon, I just do 360, remember, because the sum is 360. And I divide that by the number of sides. So that gives me 40. So this is greater than the measure of one exterior angle, so that works. Okay, and remember the sum of an interior plus an exterior angle is equal to 180. Okay, so the sum of the exterior angles of a nonagon is greater than the sum of the exterior angles of a triangle. That is not true. Any angle sum, exterior angle sum, is always 360, no matter what the shape. Okay? All right. So, now, let's find, now we're trying to find the measure of ABC. So, we need to find the figure, a regular octagon and a non-regular hexagon. So the sum of the interior angles of an octagon, let's figure out what that is. That's 8 minus 2 times 180. So that's 6 times 180. And that's 1080. Now it's an octagon, so I'm just going to divide that by 8, right, to get one interior angle, and that gives me 135. So each one of these angles is 135, right? Okay. All right. So each one of these angles, remember this square just tells us that these are 90 degrees. So this is 90 degrees, this is 90 degrees, and look right here, these two guys are the same as well. So this is 106, right? Now I need to figure out what these two angles are, okay? So I take the interior measures of a hexagon, so that's 6 minus 2 times 180, so that's 4 times 180, and I believe that's 720. And then I'm going to go ahead and subtract everything I see here. So I'm going to do 720 minus 90, minus 90, minus 106, minus 106, and I get 328. So these two are exactly the same, and I'm going to divide it by 2, right? Because I only need one of those. So this is 164 and 164. Now, it's a lot of work to get to this, but it's really not that complicated. So if we were to go all the way around here, that is a circle, and a circle is 360 degrees. So I'm going to take 360 and subtract 164 and 135, and I'm going to get my last angle. So 360 minus 164 minus 135 is equal to 61 degrees. All right, so that is 61 degrees. All right, so, oops, sorry guys. So I'm going to go ahead and stop right here because I've made this video pretty darn long. And then I will continue with our 3D figures next time. But this should hopefully get you something to get going on, and I hope it helps. So let me know if there's anything else you can do, and I can go over the first part of the packet as well. I just saw that a lot of it was completed. So I'll do the first part of the packet as well. So thanks a lot.